Episode 83, titled Class Imbalance, Why It Breaks Metrics and How to Fix Decisions, we focus on a reality that shows up in nearly every consequential classification problem. The events you care about most are often the ones that happen least. Security incidents, fraud, safety failures, and critical customer churn moments are usually rare compared to normal behavior, yet they carry outsized cost when you miss them. That mismatch between frequency and importance is exactly why class imbalance is not just a modeling detail, but a decision problem hiding inside your metrics. If you evaluate the wrong way, you can convince yourself a model is high-performing while it quietly fails at the only job you hired it to do. The goal here is to understand why imbalance breaks common evaluation habits and how to choose metrics and thresholds that align with real constraints.
Before we continue, a quick note. This audio course is a companion to the DataX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series.
Class imbalance means one class appears far more often than the other classes in the labeled data, to the point that the dataset's base rate becomes a dominant feature of the evaluation. In binary classification, this is usually a large majority negative class and a small minority positive class, though the same issue appears in multi-class settings when one label overwhelms the rest. Imbalance is not inherently bad, because many real processes are naturally skewed, but it does make naive evaluation misleading. When the positive class is rare, most examples look the same to the model at first glance, and the easiest path to a good-looking score is to predict the majority class almost all the time. The danger is that the model can appear accurate while providing almost no value for detecting the rare events that matter. Accuracy inflates under imbalance, because accuracy treats all correct predictions equally and does not care which class those correct predictions came from. If 99% of your data is the majority class, a model that always predicts the majority class achieves 99% accuracy without identifying a single minority class instance. That number feels comforting, but it is a mathematical artifact of prevalence, not evidence of learning the signal you care about. This is why accuracy becomes a blunt instrument in imbalanced settings, because it rewards the model for doing the obvious thing and hides the cost of false negatives on the rare class. When you see high accuracy paired with low detection of rare events, you are not seeing a paradox. You are seeing a metric doing exactly what it was designed to do. The right response is not to argue with the data, but to choose metrics that reflect the mistakes you actually worry about.
Precision and recall are the natural next step because they separate two different failure modes that imbalance makes painful. Precision answers: when the model raises an alert, how often is it correct? Which directly connects to false alarms and the operational cost of reviewing them. Recall answers: of all true positives, how many did we catch? Which connects to misses and the cost of letting rare events slip through. In imbalanced problems, these two quantities pull against each other because raising the threshold can reduce false positives and increase precision while simultaneously reducing recall. That trade-off is not a flaw in the model. It is a reflection of the decision boundary you choose and the base rate of the event. Thinking in terms of precision and recall forces you to confront the real tension between workload and risk rather than hiding it behind one inflated number.
When positives are rare and costly, precision recall curves are often more informative than receiver operating characteristic curves because they focus attention on performance where it matters. A receiver operating characteristic curve plots true positive rate against false positive rate, and false positive rate can look small even when the absolute number of false positives is operationally overwhelming due to the size of the majority class. Precision recall curves, by contrast, show how precision changes as recall changes, which is exactly the trade-off you face when the positive class is scarce. In settings like fraud or intrusion detection, a small drop in precision can translate into a huge increase in alerts because the model is sifting through a massive volume of mostly negative cases. Precision recall curves help you see whether improving recall requires an unacceptable collapse in precision, or whether you can gain detection with manageable alert growth. They keep the focus on positive class usefulness rather than on a ratio that can be diluted by the majority class. Resampling approaches can help, but only if they are applied at the right time and in the right place in the workflow, because leakage is a common trap. Oversampling the minority class or undersampling the majority class can change the class distribution the model sees during training, which can improve its ability to learn minority class patterns. The key is that resampling must be done after you split the data into training and validation, because if you resample before splitting, you risk placing duplicates or near duplicates of the same minority examples into both training and validation. That makes validation look better than it should, because the model is being tested on examples that are not truly independent of its training data. In a disciplined evaluation, the validation data remains untouched, and only the training data is resampled within each fold or training split. This preserves the integrity of the estimate while still giving the model a more balanced training signal.
Class weights are another technique that often fits better than resampling when you want to keep the dataset intact but change the cost of mistakes during training.
With class weights, you tell the learning process to penalize errors on the minority class more heavily than errors on the majority class, effectively making a missed positive more expensive than a missed negative. This nudges the model toward paying more attention to minority class features without artificially duplicating examples or discarding majority examples. Class weights are especially useful when the minority class is small but diverse, because duplicating minority examples can cause the model to over-memorize those few cases, while weighting encourages learning without altering the data geometry. The trade-off is that weighting can increase sensitivity and thus raise false positives, which returns you to the operational question of whether you can handle the added alert volume. In other words, class weights shift the decision surface, but they do not eliminate the need to choose a threshold that matches your constraints.
Threshold tuning is where the modeling problem becomes a decision problem, because the threshold controls how the model converts scores into actions. Many classifiers output a probability like score, rather than a hard label, and the default threshold is often 1/2, which is rarely the right choice under imbalance. If the event is rare, the cost of false negatives may be high, but the operational capacity to review alerts may be limited, so you must place the threshold where recall is acceptable and precision produces a manageable number of alerts. This is not about gaming the score, because changing the threshold changes the confusion matrix, which changes what the system does in the world. Capacity constraints mean you may prefer a higher threshold that yields fewer alerts, while risk constraints may force a lower threshold that catches more positives at the expense of more false alarms. A tuned threshold is therefore a policy choice, and it should be justified in terms of risk and workload, not only in terms of metric optimization. Choosing which metric to prioritize depends on the scenario, and it helps to practice with common cases because the exam often tests that judgment. In fraud detection, missing fraud can be costly, but excessive false positives can overwhelm investigators and damage customer experience, so you often balance recall against precision with a clear view of investigation capacity. In safety-critical monitoring, missing a true failure can be catastrophic, so recall becomes paramount, and you accept more false alarms if the process includes a safe and fast way to triage. In churn prediction, the cost structure can be different because outreach campaigns have a limited budget and over-targeting can waste marketing spend or annoy customers, so precision may matter more if interventions are expensive. The lesson is that there is no universal best metric, because the metric is a proxy for what you value and what you can afford operationally. The correct answer is the one that aligns metric choice with the real cost of mistakes.
Prevalence drift is a subtle but critical issue because it changes the base rate of the positive class over time, and that change directly affects precision and workload even if the model's underlying discrimination ability stays the same. If the positive class becomes more common, you may see precision improve at a fixed threshold because a larger fraction of alerts are true positives. If the positive class becomes less common, precision may fall, and the same threshold can generate more wasted work per true detection. This is why monitoring prevalence is not just a data quality task, but a decision support task, because it tells you whether the alerting policy remains appropriate. Prevalence drift can be driven by seasonality, changes in attacker behavior, policy shifts, or customer base changes, and it often arrives quietly. If you ignore prevalence drift, you can mistake a workload explosion for a model failure, or you can miss the fact that your precision has degraded until operations start to complain. Because thresholds translate into alerts, you should be able to communicate expected alert volume at the chosen threshold in a way that connects model evaluation to operational reality. Precision describes the proportion of alerts that are true positives, but teams also need to know how many alerts will occur per day, per week, or per batch, because staffing and process design depend on volume. Two thresholds can have similar recall but dramatically different alert counts, especially when the dataset is large and the majority class dominates. Communicating alert volume also helps clarify that false positive rate is not the same as number of false positives, because a small rate applied to a huge population can still produce a flood. When you present a threshold choice, the most responsible framing includes both performance metrics and expected workload. This closes the loop between model performance and decision feasibility. Validation under imbalance should use stratified splits so that each evaluation split preserves the class proportions as closely as possible, keeping comparisons fair across folds or repeated runs. Without stratification, one validation split might contain unusually few positives, which makes recall volatile and precision unreliable, while another split might contain an unusually high number of positives, which can make the model look better than it truly is. Stratified splitting does not solve imbalance, but it stabilizes evaluation by ensuring each fold reflects the same underlying challenge. It also makes it easier to compare different models or tuning settings because they are being evaluated under similar label distributions. In imbalanced settings, stability of evaluation is not a luxury because small changes in the count of positives can swing metrics dramatically. A stratified approach is therefore part of disciplined measurement, not merely a convenience. The anchor memory for episode 83 is that imbalance hides failure, so you must choose metrics and thresholds wisely rather than trusting default scores. Imbalance hides failure because the majority class can dominate accuracy and make trivial behavior look impressive, even when the model fails on the rare class that matters. Choosing precision and recall surfaces the real costs of false alarms and misses, and precision recall curves keep attention on positive class usefulness when positives are scarce. Resampling and class weights are ways to reshape training pressure, but they must be applied without leakage and evaluated honestly. Threshold tuning turns model scores into action under capacity and risk constraints, and prevalence drift reminds you that precision and workload can change even when the model seems unchanged. If you remember these connections, you will treat imbalance as a decision engineering problem, not just a statistics footnote. To close episode 83, titled Class Imbalance, Why It Breaks Metrics and How to Fix Decisions, pick a concrete imbalanced case and state an evaluation plan that respects the realities we have covered. Consider a fraud detection system where positives are rare, the investigation team has limited capacity, and missing fraud is costly, but drowning analysts in false alarms is also unacceptable. A disciplined plan would use stratified splitting or stratified cross-validation to keep evaluation comparable, would select precision and recall as primary metrics, and would rely on precision recall curves to understand the threshold trade-off. Resampling or class weighting would be applied only within the training portion of each split to avoid leakage, and the threshold would be tuned to meet investigation capacity while maintaining an acceptable recall level for risk tolerance. Finally, you would monitor prevalence drift after deployment because it changes expected precision and alert volume at a fixed threshold, and you would communicate alert volume alongside metrics so decision makers understand workload. When you can describe that evaluation plan clearly, you demonstrate the essential skill the exam is probing, aligning measurement and decisions when the rare class matters most.
Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.